As a calculus instructor, one of the subjects that most frustrates my students is the concept of logarithms. Now, I actually want to start not with logarithms, but with exponentials. Consider some equation like this. 10 to the power of 3 is equal to 1,000. So those three numbers, this base 10, this exponent 3, and this final answer of 1,000, are all related by this expression. But I could rearrange the order in which I express them with something called a logarithm. So in English, I read this as the logarithm base 10 of 1,000 is equal to 3. And the logarithm base 10 of 1,000 is just asking a question. It's saying, what exponent is it such that 10 to the exponent is equal to 1,000? Since we know that 10 cubed is equal to 1,000, the log base 10 of 1,000, the answer to the exponent is just 3. And so this notation is just a shorthand for asking the question, what exponent is it such that 10 to the exponent is 1,000? And it doesn't have to have bases of 10. If you're in computer science, for example, we'll often work in base 2. 2 to the 4, so 2, 4, 8, 16 is this answer. I had to check that to make sure I didn't screw it up. With the logarithm, I'm saying I'm giving you the base 2, I've given you this output of 16, your job is to find the exponent of 4. So logarithms and exponentials are both relating the same set of three numbers. It's just a question of which two numbers am I giving you and asking for the third. There's one other base that's really important for those thinking to go with calculus. This is when you use this number of e. E is a number approximately 2.7, and you can ask either exponentials with that base or logarithms with that base. And this base is special enough that it gets its own name. This logarithm is referred to as the natural logarithm. If natural logarithm is too long for you, here in Canada, we typically pronounce it ln of y. When I was teaching students in the United States, many of the students would call it ln of y. When you're talking to mathematicians and they say logarithm, they don't specify, they don't say whether it's natural. They typically mean base e. In other disciplines, often in engineering, when you just say logarithm, they mean base 10, so it's a little bit depending on context, but this is the natural logarithm. And when we go into calculus, we're going to see many, many reasons why using this particular base, this base e, actually is natural and really helpful and makes a lot of our calculus a lot easier. So I'm not going to justify why this is really nice in this video, but it really is, and we'll see that in later videos in my calculus playlist. But at the end of the day, you can use lots of different bases for lots of different reasons. And if you have an exponential, b to the x is equal to y, you can always ask the question, logarithm base b of y, which is asking what exponent is it such that b to the x is equal to y. Typically, our bases here are going to be positive. We don't want to be dealing with complex numbers, at least not for our single variable calculus coming up. Now, there is one special set of x's and y's that I like to consider, which is zeros and 1. If you have a base b that's positive, then b to the 0, when you take the exponent of 0, is always equal to 1. This is a useful point to know for exponentials, and the same is true for logarithms, switching around the 1 and the 0. Log base b of 1, you're asking what exponent of b is equal to 1? Well, the answer is 0. So logarithm of 1 is always 0. Okay, let's see how this looks graphically. Let's start by graphing the exponential function. I want to note just a couple details. First of all, that note as you go to the left, it gets closer and closer to 0, but never touches 0 exactly. But as you go to the right, it gets bigger and bigger and bigger. And if I was to zoom out and out and out, you'd see how quickly this exponential grows. And right here at x equal to 0, the exponential is 1. That was the point that we noted earlier. Plot logarithm. What I'm going to first do is plot the line y equal to x. If I plot logarithm now, the logarithm is a mirror image over that particular line, y equal to x. I can again put on this special point here, which is that logarithm of 1 is equal to 0. That's the mirror image of e to the 0 being equal to 1. But as you go along at every single spot, it's a mirror image over this line y equal to x. And as a result of that, it has the opposite behaviors. Where exponential has what we call a horizontal asymptote to the x-axis, when you flip that over, logarithm has this vertical asymptote getting closer and closer but never touching the y-axis. We can also talk about this in terms of the domain and the range. Now, the inputs of exponential, you can put in any x value you wish. And when you do these inverses, the inputs and the outputs flip. So if you're allowed any possible input for the exponential function, What do you have for the logarithm function? Well, you have any possible output. It goes all the way down to an output of negative infinity, all the way up to an output of positive infinity. The range, the set of outputs of logarithm, is the same as the domain or the set of the inputs of the exponential. And then the same is true in reverse. The range of the exponential is all positive numbers, right? It's always above the x-axis. It never touches 0, so it's round bracket 0 to infinity. That's the range of exponential. And that's the same thing as the domain of logarithm. Logarithm is not defined for any of these negative x's. Logarithm is only defined for x greater than 0, not including 0, and then anywhere off to the right. That graphical representation of being a mirror over the line y equal to x, we can formalize this by the idea of an inverse function. So an inverse function is some other function that undoes what the original function f does. So for example, if f of x was equal to some value of y, so f of x equal to y, f inverse goes the other way around, f inverse of y is equal to x. And it can't work on just the one side, it has to work on the other side as well. F inverse composed with f of x should be equal to x, and the same, f of f inverse of x should be equal to x. So f and f inverse, they undo each other, and it doesn't matter which one you do first and which you do second. If you start at x, you end at x when you do this composition. These aren't true for just any old x, they should be true for the entire domain. And specifically, the inputs of f, which means the domains of f, this is going to be all of the possible outputs of f inverse, and vice versa. The domain of f inverse is the range of f. Now, there's all sorts of pairs of a function and its inverse out there, but what we're going to use this is actually our definition for logarithm. If I start with the exponential function, then logarithm is defined to be the inverse function to our particular function. Indeed, our domain of e to the x is everything, every allowable input, and that's the same as the output of the logarithm of x, as we saw. And same for the domain of the logarithm. This is the positive numbers. Can't have any negative numbers, can't have 0 in there. That was the range of the exponential. So this is one of multiple ways to define the logarithm. It is the inverse to the exponential function e to the x. Now we have to get to logarithm rules, and there's a bunch of them, and at first they might seem mystical, but I want to explain how they're quite reasonable, and how if you forget a logarithm rule, how you can figure out what it should be. So one of the logarithm rules says that the logarithm of a product xy is the sum of two different logarithms, the logarithm of x and the logarithm of y. So somehow logarithm takes products and splits it into being sums. Now, why might this be true? To argue this, I need some shorthand for these names on the right, so I'm just going to call them m and n for the logarithm of x and the logarithm of y. And basically what my argument is every time you have a log rule, convert it to being an exponential rule and ask yourselves, what do I know about exponentials? If the logarithm base b of x is equal to m, I can rewrite that as an exponential as b to the m is equal to x. Always can go back and forth between logarithms and exponentials. Similarly, I can say that b to the n is equal to y. So now that I've rewritten x and y as exponentials, I can take the x and y and I can multiply them together. Okay, x times y is b to the m times b to the n. The point is, we have rules about exponents for b to the m times b to the n. The exponent rule I'm going to show you is actually true in general, but I'm going to show it for when m and n are positive integers, because it allows me to expand it out as a bunch of copies of b, that's m copies of b specifically, and then n copies of b again for the b to the n. So how many b's are there? Well, there's m plus n of them. So this is the same thing as b to the m plus n. And this rule is true for rationals, and it turns out irrationals as well. It takes a bit more proof, but this is a law of exponents that we can cite, that b to the m times b to the n is b to the m plus n. So if you know your exponent rules, you'll be able to get your logarithm rules. Now I just look at this simplified formula to get to what I need to do. I have it in exponential form. I just got to take logarithms. I'll take logarithm base b of both sides, logarithm base b of x times y. That's exactly what I want. But on the right-hand side I have logarithm base b of b. Remember, they're defined to be inverses. So I've got this exponential b to the m plus n, and I've got this logarithm base b. They cancel. and you just get the value of m plus n, which is exactly our rule. So the method here was just take the rule, rewrite it in terms of exponentials, use the rule for exponentials, and then put it back into logarithms. Let me do that trick one more time just to make sure that you've got the idea. I'm going to use another rule. This is the power rule now. It says the logarithm of an x to the power of y. Well, you take that y and you just bring it down at the front. It can seem like a strange rule at first. Why is this true? Well, let's do the same trick. Let's give a name to the logarithm base b of x. And then if I know the name, I can rewrite this in terms of exponentials. This is the same thing as b to the m is equal to x. Exactly what I did before. Okay, but I'm not interested in x. I'm interested in x to the power of y. So let's do that. Let's take x to the power of y. So b to the m to the power of y. And what's the exponential rule for that? Okay, again, I'll motivate this with positive integers here. B to the m to the y is just like a bunch of b to the m's all multiplied together. There's y copies of b to the m. So that's the same thing as saying that there's y times m copies of b. This is b to the y times m, and that's our general rule. I've used a rule about exponents. Now I just need to take logarithm to get back to my original, so I'll take the logarithm of both sides. Once again, I've got a log base b of a b to the ym, so let's get rid of those by our definition. So this is just y times m, which is exactly what our statement is. Okay, so we've got this power rule. We've already seen the product rule before. There's two other ones I think you should know going into calculus. There's a quotient run. I'll let you prove it. You can do it down in the comments if you like. It's almost exactly the same as the product one, but it says if instead you have the logarithm of a quotient, it's now the difference of the two logarithms. Logarithm of x minus logarithm of y. And then the final one is the change of base formula. And it says if you have a logarithm base b of x, well, you get this quotient. You can change it into logarithms no longer base b, but something else. How about base c? Logarithm base c of x, and then divided by logarithm base c of b. Now, I actually don't use this last formula very often in calculus. But the reason I like it is because this thing on the bottom is a constant. Like imagine x is a variable and it changes. We're actually talking about functions here. Logarithm base c of b is just some number. And the point is that it tells you can really use whatever logarithm bases you want. Like if you've got a b and I've got a c, we can just talk between each other by different multiples of this constant. And since we know we can do that, it allows us to be free to choose whatever base is most convenient to us. So when I said that in calculus, we almost always use the natural logarithm, we use the base of this number e, this is the formula that says that's totally fine to do. If you don't like that and want to do base 10 or base 2 or base 3 million, whatever you like, that's fine. It's just that you're going to have a weird copy of this conversion factor in a constant floating through all of your calculations. And as we'll see in calculus, a lot of the times you're just going to have a constant of 1 floating around that you can ignore, whereas if you do any other base, you have to keep this constant floating around. It's just a bit of a pain in the butt. So this change of base formula says, yeah, sure, it's fine for us to use the natural logarithm. But the top three, we're going to use them all the time in calculus.